right, so this is 13.4 and 13.5. 13.4 is going to be cross products. 13.5 is lines and planes. Both these topics should be decent length so that we can fit them both into one video. All right, so 13.4 is cross products. So in the last section, 13.3, we just talked about dot products. This is a different way. The cross product is a different way to multiply two vectors. This time, so the notation is going to be u cross v, right? So you say u cross v, and you always use the cross symbol just to distinguish it from the dot product. This time, this guy here is a vector, right? So in a way, part of the reason we found the dot product slightly unsatisfactory was because the dot product u dot v turned out to be just a number as opposed to a vector, which you kind of don't like because, you know, normally when you work with numbers, 3 times 5, 3 and 5 is a number, and 3 times 5, 15 is also a number. So it's slightly weird to have the product of two things turn out to be something else. In this case, the dot product is, of two vectors is indeed a vector. However, there's a lot of other issues with the cross product that we're gonna talk about. Okay, let's see. So something interesting about, before we even talk about what it is, something interesting about the cross product is that it only exists in 3 dimensions. Only exists in 3 dimensions. Well, actually, in reality, and 7 and 8. But we're obviously not going to worry about those two. So in terms of our class, that means that there's not going to be any cross products in terms of vectors in the plane. All right. So you have to have 3 entries to be able to do a cross product. So that's one limitation. And of course, if you're thinking ahead in the future, when you might be working with vectors of many entries, there's going to be no such thing as the cross product. Whereas if you think about the dot product, you can easily extend it to multiple dimensions of any size, and in fact, even infinite dimensions, if you like. And that's actually kind of slightly what the extra credit problem on the homework was about, on the paper homework. Okay, so we can already see that there's some issues with the cross product. Nevertheless, we do talk about it because it's able to represent a lot of real life features that we see, for example, in physics. So it actually turns out to be quite useful. Okay, so there's again going to be 2 kind of definitions of the cross product. We're going to have a geometric definition, and we're going to have a more computational or algebraic definition. With the dot product, I started out with the algebraic one because actually that's the one that is more natural. For the cross product, things are a little more complicated because the cross product is, in a way, and if you think about it correctly, it's kind of unnatural, at least the way we're discussing it. So I'm actually going to start out with the geometric definition. Okay, because it's probably more approachable for this example. The algebraic one is going to be kind of a mess in a way. Okay, anyway, let's see. So u cross v. How do I define it if I have 2 vectors u and v? Again, these have to be vectors in space. So u cross v is a vector. And what's a vector? A vector is a length and a direction. So the way we're going to define this is we're going to define each piece separately. And then, of course, we just put them together and we've got our cross product. Okay, the length In terms of a formula, it's relatively simple. That's going to be the length of u, length of v, and then sine theta. So this is in contrast to the dot product, where it was a cosine theta instead of a sine theta. Okay. All right. Why do we care about this particular quantity? We'll see. It gives us some interesting applications or useful applications. Okay, the direction is going to be a little more difficult to explain on a screen here. Normally, I would do this. If this was an actual lecture, I would do this in 3D, obviously, with my hands. But now I'm going to have to try to draw a hand. Okay, we'll see. So let's say U looks like this and V looks like this. All right. So this is in space. Okay. So what's the direction of the cross product? Well, if I look at it in space like this, without any nice perspectives or anything like that, it's really hard to draw. So what I'm going to do is I'm going to take a look at the plane that U and V create, right? So two vectors create a plane, and let me just draw that down here. Okay, so it's maybe like this. Okay, so what you're supposed to do to figure out the direction is, well, first of all, the direction. One of the most important features is it's perpendicular to both U and V. Okay, so the direction is going to be a vector that's perpendicular to both U and to V. All right, now the issue is actually that there's two vectors perpendicular to both U and V, right? So let me go back to this 3D picture here. In terms of this 3D picture, it looks like maybe this guy here is perpendicular to both U and V, right? Let me draw the 90 degrees. But also this second vector down here, the opposite direction, is also perpendicular, right? So the only real question is, once I've said that it has to be perpendicular, the question is which one of these two, right? We need some sort of nice algorithm or nice procedure to be able to figure out which one of the two vectors it should be. So the procedure is called the right-hand rule. Rule. And what you do is, I'm going to try to draw this. You take your right hand, and it has to be your right hand, so that the blade of your hand is along. So we're doing U cross V. So U comes first, and then V. U cross V. So you put your blade of your hand along U. So this here, let's say, is your pinky. This one is your ring finger, middle finger, index finger, and then here's your hand. I guess maybe do this in a different color here. So pinky, middle, ring finger, this is your middle finger, that's your index finger. So here's your hand, right? So the blade of your hand right there is along the U direction. Okay. So your thumb is going to be, so you have to place your hand so that your thumb, or so that when you curl your hand, when you curl your fingers inwards in towards a fist, that they curl towards V. All right? Because actually there's two ways to place your hand. You can place your hand the way I've drawn right here, or you can place your hand down here like this, right? And in which case, when you curl your hand, it would actually curl the other way. Okay? So you want to place your hand so that it curls towards V. So that when you close your hand to a fist, it curls towards V. Okay? Now, when you do this, your thumb, if you do this correctly, right, in this red picture here, your thumb is going to be pointing, if you stick your thumb up vertically or perpendicular to your fingers, your thumb is going to point in this picture like that. Okay? the direction that your thumb points is the direction of u cross v. Okay, so in this picture, straight upwards like that. Okay, in our previous picture up here, the whole 3D picture, it's going to be the red vector. Okay, all right. It takes a little bit of getting used to, but after a bit, it's not too hard. Okay, so direction equals use right hand rule. All right. It has to be the right hand. If you use your left hand, you're going to get the negative of the correct direction. All right, and if you use your left hand and you do the exact same procedure with your left hand, you're going to get the opposite direction. Okay, so I guess if you want, you could do your left hand. Just remember, it has to be the opposite direction that your thumb is pointing. Okay, that's it. That's the cross product, right? We've described what the length of the cross product should be. We've described the direction. So put that together and we've actually got a vector, at least geometrically. Okay. All right. Let me do another example just to make sure we're all okay with this. X, Y, Z. And let me do a kind of a simple example. Let's do, so remember our vectors I, J, K. So this is I, and that's K. What's I cross K? So it might be a good idea to pause right now and try to see if you can do the right-hand rule correctly. But it turns out that it's going to be minus J. All right. So if I did do this kind of hand procedure, I would have to kind of twist my hand so that this is my pinky there, right? This is my ring finger, my middle finger, index finger, right? So this would be, this picture's not so great. Let me start it over again. So what would happen is the back of your hand, if you were actually to do this, the back of your hand would live on the XY plane, would be kind of on the XY plane. So maybe let me draw it like this. Okay, those are your fingers. Here's your hand. The palm of your hand in this example, in this picture, is actually facing straight up. All right, and your thumb. So when I do curl my hand in this, my fingers in this way towards a fist, you can see that it curls towards the z-axis, right? It's going to curl towards the z-axis. And in this case, my thumb is going to be, if in order to do this, my thumb is going to be pointing in that direction. Okay. All right, so I cross J is going to be, I cross K is going to be equal to minus J. Again, it feels kind of weird doing this, and sometimes you might have to contort your hands to kind of get it to feel right or to be correct. But after a bit, you get pretty used to it. All right, we'll talk a little bit more about the basic I cross J equals what, I cross K equals what, K cross J equals what, and so on in a few minutes. But before we do that, let's talk about an issue. So I said that the direction is going to be, or a potential issue. Direction of U cross V is perpendicular to both U and V, right? Well, does that always work? If U and V look like this, right, no problem, right? So we can kind of even see in this picture, it's going to be, the dot product is going to be that, right? But, oh, sorry, the cross product. But what happens if U and V are parallel? So what happens if this is U and that's V, for example? Then our description for the direction is not going to work because, first of all, well, our right-hand rule is not going to work. There's no curling anywhere because the two vectors are the same, right? But even in the description of perpendicular to both U and V, that doesn't work because there's an infinite number of vectors perpendicular to both u and v, right? In fact, there's a whole plane's worth of vectors perpendicular to both u and v. This guy's perpendicular to both u and v, that guy's perpendicular to both u and v, that guy's perpendicular to both u and v. Let me draw the kind of perpendicular symbol, right? A lot of vectors are perpendicular to both u and v. So if it's on the face of it, it seems like there's something wrong with our definition. However, everything actually works out because this is not a problem. Because what's the length of the dot product, cross product? U cross v, the length is, again, I'm just writing down our definition, uv sine theta. Well, if two vectors are parallel, or let's say, for example, in this picture, literally in the same direction, then what we're going to have is theta equals 0. All right? And so sine theta is going to be 0. And so the length of the cross product is going to be 0. And so the cross product is going to be 0 if same direction. Okay? 0 vector. And so the description of the direction in the right-hand rule, the fact that it doesn't work doesn't matter because it's the 0, it's forced to be the 0 vector anyway by this sine theta. Okay? And of course, in the opposite direction, u cross v, if u and v are in opposite directions, equals 0 if u and v are in opposite directions. Also, right? Because in opposite directions, here's u, here's v. What's the angle? Pi, right? Sine pi, 0. So again, that's a situation where potentially you're not able to talk about the vectors perpendicular to u and v because there's an infinite number of them, right? So you're not able to pick out the correct one using the right-hand rule, but it doesn't matter. U cross v is 0. Okay. So parallel vectors, u and v, if they're parallel, then their cross product is 0. Okay. All right. By the way, this might hint to you that one way to tell whether two vectors are parallel is to take their cross product, but in practice, that's probably more work than is necessary, right? If I do ask you, are u and v parallel, right? That's actually just a simple question of algebra, right? If u is let's say a, b, c, and v is d, e, f, right? Are they parallel? Well, for them to be parallel, one has to be kind of either a stretching of the other or a shrinking of the other, right? So in other words, if they're parallel, then you would be able to solve, right, a times something. Let me not do times something. Let me give a variable name. A times, let's say, t equals d. B times same number t equals e. And c times same number t equals f, right? If you can solve this set of three equations using the same number t, then they're parallel. Okay? If you can't, then they're not parallel. So actually, it's the idea of whether, or the question of whether two vectors are parallels is actually simpler than having to bring in the concept of the cross product. By the way, this is kind of interesting because this question of whether two vectors are parallel, you can see you have to solve a system of equations that has three equations, but only one unknown, right? You have the unknown t, but you have three equations. And one of the general principles of math, it's not necessarily always true, but the general principle is that when you try to solve an equation, a set of equations, if there's more equations than unknowns, then generally there's no solutions. Okay? And what that means in terms of our setting here is that generally two random vectors are not parallel, because generally, again, this set of equations has no solution. Okay? So it has to be a very special situation for there to be a solution, right? Which makes sense. because it's a very special situation for you to pull out two vectors out of thin air and actually have them by luck be parallel. Okay, so that's a very useful general principle in math. Again, if you have more equations than unknowns, generally there's no solutions. All right. I guess I should make this more complete. If you have more unknowns than equations, on the other hand, generally there's going to be an infinite number of solutions. All right. Okay, and if the number of equations you have is the same as the number of unknowns, then it's a little bit more fuzzy. Oftentimes, let me just say it like this, oftentimes there's a finite number of solutions. Okay. Let me write down some properties of the cross product, and we'll immediately see that some things are kind of not so pleasant. So the first property is that u cross v is not equal to v cross u. Okay. So this is already unpleasant because we're used to multiplication where 3 times 5 is the same as 5 times 3. But this is definitely not the case for the cross product. And we know this because u cross v, let's just draw a picture here, u cross v. If I did u cross v, then I would get this direction vertical upwards, right? So u cross v would be pointing in this direction. And on the other hand, v cross u would be pointing in that direction. Okay? So they're definitely not equal. However, it's not like there's no relationship between them. They're in opposite directions, and they have the same length, of course, because both of their lengths are length of u, length of v, sine theta. All right? So they're the same length, but they're in opposite directions. Okay? So they're not equal, but it's not like it's they're completely different from each other. Okay. The second kind of slightly unpleasant property is that u cross v, if I do this first and then I cross it with a third vector w, that's not necessarily equal to u cross v cross w, where I do the second two first. All right. So the order actually matters. So if I do u cross v first, I take the result, which is a vector, and then I cross it with w, I'll get a vector, but that vector is not necessarily going to be equal to the same one if I do v cross w first and then I cross the result with u. All right. Again, this is unpleasant because normally, right, 3 times 5 times 10, it doesn't matter whether I do the 3 times 5 first or the 5 times 10 first. Here it matters. Okay. I think maybe it's a nice exercise to try to find 3 vectors where you can explicitly see that this doesn't work. All right. In terms of the definition that we have right now. All right. So just do it in terms of curling your hands or whatever. Try to figure out an example that doesn't work. Okay. When we actually do the algebraic version of this, then it's going to be easy to find an example because this pretty much is always true. It's pretty much never equal. So if you just make up 3 vectors randomly, and then try to compute the left-hand side and the right-hand side, there's almost no chance that they'll be equal. All right. But before we even see that, try to find an example just graphically using your hands to do the cross product to see why this might not be true. It's a nice little exercise. Okay. So by the way, I guess I should say words. This is usually this first property. If it were equal, we would say that the cross product is commutative, but here the cross product is not commutative. All right, so not commutative. All right, and here, so things not being commutative is not so great, but actually there's a lot of mathematical objects which are not commutative. So it's not the worst disaster. However, The second one is called not. So if this were an equality, the second guy here, it would be called, this property would be called associativity, right? We would say, if it worked, we would say the cross product is associative, but it's not, so not associative. All right, so not being commutative is not great, but oftentimes a lot of math involves objects which are not commutative. But not associative is actually really bad. It's a kind of a very fundamental property of mathematical multiplications. Let me say it like that. And for it not to be associative is pretty bad. Okay, maybe if you've done, so like I said before, some universities do a linear algebra class before calculus. And if you have done that, then you'll know that, you'll know an example of this not commutative situation, and that's matrices, right? A times B, if A and B are matrices, is not equal to B times A most of the time, right? If you haven't seen matrices, next semester or next quarter, you'll see the example, A times B and B times A as matrices, not commutative. And yet matrices are perfectly okay things to work with. Okay, by the way, something interesting in terms of this not being associative, that means that you're not allowed to write something, or not that you're not allowed, but it's kind of dangerous to write an expression just like this, right? Because it's not clear, if I just write this, it's not clear whether I mean for you to do this first, or whether I mean for you to do this first, right? And that ambiguity can obviously cause problems. So if you are going to be in a situation where you're going to be doing multiple cross products, you should be disciplined and put parentheses to make sure it's clear which ones you're doing first. Okay, because again, they're definitely not going to be equal. All right, and it's not going to be a situation where, you know, in the commutative situation, they're not equal, but they're kind of just opposite directions. So it's not a big deal, right, in a way. But the cross product, they could be not equal in very dramatic ways. Okay. All right. So those are kind of the two unpleasant properties of the cross product. But as usual, we do have properties that that do work out well. So let me write out some properties that are okay. So A is a number, scalar, U cross V. This is equal to AU cross V, which is also equal to U cross AV. All right, so what this says is if I have the cross product of two vectors, I can cross them. If I have two vectors, I can cross them first and then scalar multiply to the result. That's the same as if I scalar multiply to one of them first and then I do the cross product. Okay. If you think about the geometric definition, it's pretty clear that this should be true, especially since, for example, the definition of the length means that this A, you're just going to have an absolute value of A come out in terms of the length for all three of these expressions. So the length is definitely not going to change. Okay, and either is the direction, right? This guy here is only going to change the direction if A is negative. And if A is negative, it's going to change the direction on the left-hand side. It's going to change the direction here, and it's going to change the direction here. So all three, everything is consistent. Okay. Next one. So this one is kind of what you would expect. So this is a good property. The next one, we talked about the dot product, and we said the dot product satisfies the distributive law. Well, any decent concept of multiplication will satisfy the distributive law, and the cross product does. Otherwise, we probably wouldn't even call it a product if it didn't. So U cross V plus W, that's kind of the characteristic of if you are going to define a product. If you let me say it like this: if you have the concept of addition, and then you want to add on top of that the concept of multiplication, then a decent concept of multiplication relative to that addition should satisfy the distributive law. Okay. That's a little bit more precise. All right, in any case, I pretty much hinted the distributive law does work. U cross V plus U cross W. So you could do the addition first and then the cross product, or you can do two cross products and then add. All right. Okay, this one I'm not going to explain why it's true. Probably it's easier to see why it's true once we talked about the algebraic definition of the cross product. All right, next one. There's actually going to be two. Sorry if there was a strange cut there. I stopped recording by accident, and hopefully I'll be able to stitch the two videos together. Okay, what was I saying? So, well, we've got this distributive law, and we also have if we do it the other way, this is also what you would expect, or what you would like. All right, and again, both of these guys, both these distributive laws are easy to verify once we do the computational or algebraic aspect of the cross product. All right, again, these two are why we call it a product. Okay, let's actually go to the computational aspect. So how do we actually do the computations? So there's two ways. One way is going to be always going to work. The other way is probably works, or you'd probably be more comfortable with it if you've already done some stuff in linear algebra, some matrices stuff. So the first way is going to be the idea behind the first way is that we know we can write every vector in space, right? Can be written as something 3i plus 4j plus 5k, something like this, right? So if we have if we want to take this cross product with a second vector, 2i minus j plus k, right? Because of the properties above, right? One thing we can do is we can rewrite this expression using the properties above. U cross V is equal to 3i plus 4j plus 5k cross 2i minus j plus k. All right, using the laws from above, well, they basically tell us that we can do this cross that, cross that, cross that, and then the 4j cross the three guys, and then the 5k cross the three guys. All right, so this is actually going to be 3 times 2, and then I cross I. This is going to be pretty brutal, but the computation is relatively straightforward, so at least that's we have that going for us. Minus 3i cross j, so that would be 3i, and then cross the minus j. And then plus 3i cross k, right? That would be the first guy here, cross the k in the second vector. Okay, and then let's see, plus, and then we go to the 4j. 4j cross 2i times 2, j cross I. And then minus 4, j cross j. And then plus 4, j cross k. And then plus, now we go to the 5k. 5k cross 2i, so 5 times 2, k cross I, minus 5, k cross j. And we always make sure to keep the order correct, because the order matters, right? So this is k cross j as opposed to j cross k. And the last one is k cross k, so plus 5, k cross k. All right. So it looks terrible, but the first thing we remember is that if you cross two vectors that are parallel, you get 0. So in reality, we didn't even have to bother with this term, or that term. Okay. All right. Now here's the point. What you can see is I cross j right there, I cross k right there, j cross I, j cross k cross I, k cross j. If we know all of these individual pieces, right, then we can compute the cross product. So you're just breaking down the cross product into that kind of I, j's, and k's. And if you kind of sit down and understand how to do the cross products of the i's and j's and k's with respect to each other, then you're all set, right? So this is just an easy breakdown of the cross product. Okay, so what are all these I cross j's and I cross k's and all that business? Well, you could do this the brutal way and use your right-hand rule, right, to figure it out. But I cross j is equal to k, and that one's the easiest, right? So x, y, z. This direction is I. This direction is j, right? If you put your right hand, let me try this picture again. You do your right hand here, right? You curl your fingers towards the y axis. Your thumb is going to point up. So I cross j is k. Okay. The length is 1 because, of course, the length of I cross j is length of I, which is 1, times length of j, which is 1, right? And then I and j are perpendicular, so sine of theta is 1, right? So I cross j is something times k. From the right-hand rule, it's something times k. And from the actual computation of the length, it's 1 times k. Okay. Okay. Now we already said that if you know this, then you know j cross I, right? That's equal to minus k. Okay. And I highly encourage you to kind of contort your hand so that you can actually see this in terms of the picture. Do it, at least a couple times just so that you're comfortable with the right-hand rule. Okay. So in fact, we don't have too many of these that we need to write down, right? If we know I cross j, then we know j cross I, right? So for example, in terms of our computation above, right, we know this guy right here. And automatically we know that guy right there, right? Okay, and now let's just go through. There's really only 3 of them, right? J cross k, that's going to be I, all right? And again, I encourage you to contort your hand to actually see this. I'm not going to try to draw a picture this time. And of course, because of this, right, k cross j is equal to negative I, right? And in terms of our computations above, j cross k, that means we've covered this guy and we've covered that guy. So there's only one more. Sorry, did I check the wrong ones here? Yeah, I guess I did. So the first one was I cross j. So I guess I checked the I cross k. So I checked this one, and I should be checking this one. Okay. All right, so the last one is I cross k or k cross I, right? So I'm going to write it as k cross I is equal to j, and alternatively I cross k is equal to minus j. And again, I encourage you to, at least once in your life, right, contort your hands to do all 6 of these, just to get used to the cross product. Okay, the ones, probably the easiest way to remember these so that you don't have to contort your hands every time is to remember this one, and to remember this one. All right, and how do you remember these? It's actually super easy. You just have to remember the ordering I, j, k. So this one, the first guy, I, j, k in order. All right, the second one, I, j, k in order. Right, the third one, I, j, k in order. Okay, so whenever the I, j's, and k's are in order, then the right-hand side is going to have a positive sign. All right, so it's super easy to remember. And if you change the order, right, so for example, this second one here is not I, j, k, it's I, k, j. Because of that kind of misordering, you can remember that there's a negative sign right there. Okay, that's just there's no, I mean, there is kind of some math behind it, but for at least for our purposes, it's just a nice way of remembering how to do the cross product. Okay, in any case, that means we're all set for the computation above, right? I guess I should just actually complete this computation. So ultimately we have I cross j is k, so minus 3k. I cross k is minus j, so minus 3j. J cross I is minus k, so that would be plus 8. Sorry, I guess minus 8. K. And then for the next three, we have j cross k is I, so plus 4i, plus 10j, and then plus 5i. Okay. Just using these 6, or basically only using those 3. Maybe I should actually combine them just to, again, complete it. 5 and 4 is 9i. Minus 3 and 10, 7j, and minus 11k. Okay, and you can always check your answer. This guy here should be perpendicular to both u and to v. All right. That's actually one of the major applications for the cross product. It allows us to find vectors that are perpendicular to two vectors that we already have. Sounds like why would we care about that? But it's surprisingly useful. All right. Okay, so let me see. 3, 4, 5, 9, 7 minus 11, 3, 4, 5, 27, 28. Yeah, looks like it's going to be okay. All right. So it looks like I didn't make any silly mistakes here. Okay, so this is a really nice way to compute the cross product because you're just boiling it down to simple multiplications and then just having to remember 3 simple cross products. I cross j is k, j cross k is I, k cross I is j. All right. Okay, now the second way to do the same computation is kind of based on matrices, or at least the procedure that you've possibly seen when you work with matrices. And the idea is if we have, again, let me write down my u was, I think it was 3i plus 4j plus 5k. And my v was, sorry, let me check. 2 minus 1, 1. 2i minus j plus k. Right? So the way, another way to compute is to do this. So you write I, j, k, and then you put u as the second row, 3, 4, 5. V as the third row, 2 minus 1, 1. And you think of this as a matrix, and we use the just the straight vertical lines because what we're doing is we're taking the determinant of this. Okay. And that's it. That's going to give you the cross product. So if you knew what the determinant was, you're all set. But if you don't know, let me actually do it for you. So what you do is, so this determinant thing is something you use in matrices. It's actually very useful in terms of theoretical properties of matrices in linear algebra. But we don't really care. We just want to be able to do the computation. So what is this? How do you compute what vector this is? What you do is you cross out the first row and you cross out the first column. All right. So when you do this, I've ended up crossing out twice, right? Both row and column, the I. So the first thing I want to write down is I. Okay. Now, the stuff I haven't crossed out is this 4, 5, minus 1, and 1. And what I'm supposed to do is multiply the 4 with the 1, and then minus this times that. Okay, so this is going to be 4 times 1 minus 1 times 5. All right, that's going to be my first term. That's going to be my I term. All right. Okay, no problem, right? Because this guy here is just a number. In fact, it's going to be 4 plus 5, which is 9. Okay. All right, next. we're going to do the same thing. We're always going to be crossing out the first row. So we cross out the first row, and now we cross out the second column. Okay, if we do that, then we've crossed out the j twice. So the next term is minus j. Okay, so it goes plus, minus, plus. All right, and if there were more, if we were doing kind of something in terms of matrices, it would just alternate, plus, minus, plus, minus, plus, minus. Okay. All right. So if I did do this crossing out, just the blue crossing outs, I would be left with the 3, the 5, the 2, and the 1. All right. And then what I would do is I would multiply, same idea, 3 times 1 minus 2 times 5. Okay. And that's it. That would be my j term. So 3 times 1 minus 2 times 5. Okay. All right. What is that? That's 7. Minus 7. Okay. And then, of course, remember we have this minus sign out here. All right. And then lastly, we would cross out, I guess I need a different color here. Lastly, we cross out the first row, and then the last column, we're left with the k. So, or we've crossed out the k, so k. And then the non-crossed out terms are the 3, 4, 2, and 1. So we multiply the 3 to the, we multiply the 3 to the 3 to the minus 1, 2 to the 4. All right. And we subtract. So this is going to be 3 times minus 1 minus 2 times 4. Okay. That's going to be minus 3, minus 8, so minus 11. So ultimately, we get 9i plus 7j minus 11k. And hopefully, this is the same as what we got above. 9, 7 minus 11. 9, 7 minus 11. Perfect. Okay, so either way is fine. If you are used to working with matrices, this second way is really fast. But if you've never seen matrices before and you think you might make a silly mistake in remembering this procedure, do it the first way. Okay, either way is fine. Okay. All right, by the way, when I said you can confirm the distributive law properties or the associative or the other properties that we talked about that were true, you can confirm them using our algebraic computational aspect of the cross product. What I meant was confirming it using this method, right? You can't confirm it using the first method because the first method actually used the property, right? We used the distributive law actually to do the first step. So obviously you can't confirm a property using that property, right? So what I meant was use this procedure. This is actually the more standard. The second one is the more standard way that cross product is often described. But I know a lot of people haven't seen determinants before, so I think a lot of people might be more comfortable with the first method. Okay. Let's see. So let me talk about applications. So one thing we notice, just like with the dot product, that the cross product is easy to compute. Right? If I give you u and I give you v, this guy here, you just follow the algorithm. Right? Just follow the algorithm, either one of the two. What I mean is, of course, if I give you these guys in terms of actual vectors, right? 3, 1, 3, and then 4, 2, 0, whatever, right? If I gave you the actual coordinates or the actual descriptions of these vectors, the cross product is super easy to compute, right? It takes a little bit of time, but in terms of how much math knowledge you need, pretty much none, right? So easy. So what that means is, just like with the dot product, we can use this fact to understand properties of the interaction between two vectors using this computation. All right. So what I mean is we know u cross v by the official kind of picture definition is uv sine theta, right? We know this guy is easy to compute, right? So that means that we can, again, just like with the dot product, we can understand products about the features about the relationship between u and v, okay? Oh, by the way, how do you reconcile the two different definitions? You just do some trig, right? Just like with the dot product. I'm not even gonna consider going through that. Okay, so let's see an application of the fact that the cross product is easy to compute. So let me look at this. Let's look at a picture example. U, V. Let me look at this. So I'm going to fill in this parallelogram like that. And I'm going to drop this perpendicular down like that. I'm going to write down, again, when we have two vectors, we're often very interested in this angle theta. And we are today because sine theta appears in the cross product. Let's see what this uv sine theta means. All right. So if I look at this picture, I can see that this this diagonal, or sorry, this dotted line that drops down as the perpendicular, what is its length? Well, I've got a right triangle, there, there, and there. I've got the side of the hypotenuse is length v. So sine of theta is equal to the thing that we don't know over length of v. And so the length that we don't know is length of v sine theta. Okay. All right. Why do I care about this? Well, notice this. What happens if I multiply this thing that we don't know? Well, we do know it now, but whatever. Times the length of u, right? That gives me length of u, length of v, sine theta. And what is that? That's the length of u cross v, which again, that's easy, right? Now this right-hand side, what is that? It's the length of this guy right there, and then times the length of that guy right there. So we've got a parallelogram. This is the base, that's the height, right? If I multiply these two together, that's actually the area. Okay, so the deal is, if I need to calculate the area of a parallelogram, super easy, right? I just, if I give you a parallelogram, let's say with coordinates, right? I give you this coordinate, and this coordinate, for example. I don't need the other one. Then I can create a vector here. I create a vector here. I call this one u. I call that one v. I calculate u cross v, and I'm done. Right? And again, calculating u cross v is easy. Okay. So one application of this cross product is that we can calculate areas of parallelograms very easily. Okay. All right. On the homework, I think if I remember correctly, the online homework, there's a problem where you have to do something like this, or maybe it was you calculate the area of a triangle, right? So they give you 3 points. What's the area of the triangle? Well, no problem. Just create a parallelogram, and then you calculate the area of the parallelogram. Half of that is the triangle that you want. Okay. All right. So that's one application. Now, at this moment, you think, who cares, right? Why would I care what the area of a parallelogram is? We're going to care. We're going to care because it's going to be really important for us when we do integration on kind of more complicated surfaces in the near future, 4 weeks or so from now. Okay, maybe five weeks or so. So it seems ridiculous. Who would want to need to, or who would need to calculate areas of parallelograms? We need it. Okay. So that's one application. That's one mathematical application. Actually, it'll turn out to be quite important. Another application is torque. from physics. So here's the idea. Let's say I have a bolt here. Let me try to draw a bolt. Okay, and I have a wrench. So this is a very, very standard example. So I have a wrench, and I'm turning this wrench. All right. So let's say I'm turning this wrench in that direction with with a certain amount of force. Let me draw that vector again. In this direction with a certain amount of force F. Okay. Let me say that this, I'm going to need, let me do it in a different color. I'm going to need this vector right there all the way to the point at which I'm turning. I'm going to call that R. All right. Okay, now, when I do this, when I apply this force to the wrench, right, the wrench is going to be turning. Once I apply this force, it's going to turn in this direction. It's going to rotate in this direction, right? Because the bolt is fixing this this end of the wrench. Okay. Now, just like with the dot product, we're applying this force kind of in a skewed direction, so that some of the force that I'm applying actually is in a way being wasted, right? Because this wrench is rotating about this center point right there, the force that actually is doing something when I turn this, when I apply this force, is the force, part of the force, which is perpendicular to R. All right. So the force that actually, the part of the force that actually matters is actually going to be, sorry, in that direction. Okay. The other part of the force, I guess, let me actually draw the actual part of the force. So, oh no, sorry. What did I erase there? Okay, sorry. The part of the force that actually matters, the literal vector part of the force that matters is that vector right there. Okay. The other part of the force you can see is going to be this one, this vector. And you can understand that it doesn't matter because it's going parallel to R, right? So it would be kind of force, which is moving the wrench away, in this example, away from the bolt. So it doesn't do anything in terms of turning the bolt. All right. Okay, so the question is, how much of the force that I applied just matters, right? So what is the length of that vector right there? That's what I want to know. Okay. All right, so in this setup, let me redraw the picture with the vectors arranged in a slightly different way. So let me draw R right here. And let me draw F right there. All right, so all I've done is I've moved the vector so that they have the same base point. Okay, the vector that matters, or the length of, let me say the vector that matters is this one right here, right? And again, it's perpendicular to R. Okay. All right, so that, let me draw it also here. Okay, let's see. The angle between my two vectors, theta, is right there, right? The usual angle between the two vectors that we've been working with day after day. So what is the length of this guy right there? And again, it's the same computation we've been doing over and over again. So we have a right triangle. We have the hypotenuse is known to be length of f, right? The guy we don't know is the opposite side. So we look at sine of theta. That's equal to the guy we don't know, length of f. And so the guy we don't know is length of f times sine theta, or at least the length of the guy we don't know. Okay. All right. So that's how much of the force that I've just applied to this wrench worked to turn the wrench, right? The rest of the force is, in a way, just doing nothing, at least in terms of turning the wrench. Okay. All right. Now the torque is, well, okay, let me say something like this. When I'm turning a wrench, right, we've all done this before. If I turn the wrench using a long wrench, maybe like in this picture above, compared to a shorter wrench. So if I had a shorter wrench, right, it takes a different amount of force to turn the bolt, just from physical experience, right? It takes a different amount of force to turn the bolt the same amount, right? It's easier to turn the bolt when the wrench is longer than if the wrench is shorter, right? So not only does the force matter, just in practice, right? We know this. Not only does the force that we're using matters, right? Or the part of the force perpendicular to the to this direction r here, but also how far we are, right? So we have this concept of torque, where which measures kind of how much force, rotational force, is being applied to the nut. All right, and what is that? That's actually the actual force that matters, and then times the length of the length of r here. All right, so the torque. Let me be a little more careful. The length of the torque, because the torque is going to be a vector. The length of the torque is going to be r f sine theta. Right? And again, this all makes sense because this guy here is how much of my force matters. And this guy right here, this r, it matters because the longer the wrench, the greater, the easier it is. So in a way, the greater rotational force we're applying to the nut. Okay? So that's going to be the torque. And what is that? That's nothing more than r cross f. Length of r cross f. All right? Okay, so this cross product allows me to describe rotational force, in short. Okay? All right. I said the torque is actually a vector. What's the direction? Well, the torque direction is actually the same direction direction of r cross f. All right, same direction. So in other words, torque is equal to r cross f, right? Same length, same direction. Okay. All right, so that's a nice, very nice physical concept that we see, that we can describe using using the cross product. Okay. Oh, by the way, why should torque be a vector, right? Why can't we just settle with the length, right? That seemingly maybe gives us enough information, right? But it doesn't, because if I rotate the opposite direction, right? Just now in my example, I've been rotating in this direction. If I rotate in the opposite direction, right? Very different things are happening, right? In one direction, I'm loosening the bolt, right? In the other direction, in terms of the physical example, in the other direction, I'm tightening the bolt. So it actually does matter, right? One way I'm rotating counterclockwise, the other way I'm rotating clockwise. And so what the direction of the torque tells you is the direction that I'm applying my rotational force. All right. So in the example that I have been doing, right, this is my R. This is my R, right? That's my F, or at least a part of the F that matters. So doing the right-hand rule with the third axis coming out of the screen, my torque is going to be pointing out towards the screen. Okay, out towards you. Let me say it like that, out towards you. Okay, and if I rotated the opposite direction, if this was my new F, then my my torque would be into the screen. All right. So this direction allows me to describe which direction I'm turning. Okay. So very nice and complete description of rotational force. Okay. I think we've done a total of an hour here, so maybe I should do the 13.5 in a different video. Actually, one thing you can let me know if you come to the Zoom meeting on Thursday is, would you rather have longer videos that have multiple sections in them, or smaller videos of fewer sections? I think an hour long is good though. So maybe I'll stop this and then I'll do 13.5 as a separate video.